Hey everyone, today we'll be talking about functions whose mappings are defined by rules. Now, if you watched my last video, you might have found yourself asking, what's the point, right? What is this function thing, these mappings that I'm drawing, what do they actually help us do? And you'd be right to ask, because without additional machinery, the function as I described it in my last video can't actually do what it's meant to do, which is act as a tool for describing the relationships between two different sets. For example, let's say we know a guy named Bob whose mom gave birth to him when she was 27. We'd like to be able to write a function that describes the relationship between Bob's age and his mom's age, that takes in as an input some age that's meant to be his mom's age, and inputs what Bob's age will be at that moment. So let's start. We'll have f, and we know the input set should be numbers more than 27, because only those numbers will give us a valid age for Bob, and it should map those ages to Bob's ages, which will always be positive. So the output set will be positive numbers. Now, before I try and write down the mapping itself, let's just informally describe what each number is going to go to. So each input should be mapping to every output that's 27 less than it, right? So we'll say f sends each number to the number 27 less than it. And that's, an informal description of how this mapping is going to go. It's a rule that describes where each number goes. Now, formally, I could do what I did in the last video and get these big boxes in here to describe the input and the output set. And I'll write, 28 goes to 1, 29 goes to 2, and so on, so on, so on, so on. Now this would take forever, literally forever, if we're allowing fractional ages. It's cumbersome, it's, time consuming, but most importantly, it doesn't add more to our understanding of the situation. This informal rule on the left side already describes everything we need to know about this function. So drawing it out in this mapping format, as I described in my last video, doesn't help at all. We'd like to have, in fact, this informal rule just be able to formally define our function. And of course, there's ways to do that in the language of mathematics. In fact, there's a couple. The most common way you'll see is f of x, the input, equals x minus 27. So x is going to the number that's 27 less than it, as we described. Another way you'll see this written is x goes to, with this weird arrow with a horizontal base, goes to x minus 27. But this is much less common, so just be on the lookout for the first description. And so this rule, combined with our description of our input set and our output set, is a full formal definition of a function. Let's do another example. Suppose we want to write a function to describe the relationship between the area of a square and its perimeter, and we want to write the perimeter in terms of the area. Okay, so we'll call this function p for perimeter, and it's going to take in areas which are positive numbers, so the input set will be positive numbers, and it's going to send them to perimeters, which are also positive numbers. So the output set will be positive numbers. And once again, let's informally describe what this mapping is going to look like. So first we want to take the square root to get the side length. So take square root. And then we want to find out how long 4 side length is, right? Because the square has 4 sides, and so its perimeter is going to be 4 times one of its side lengths. So multiply by 4. And that's our informal description of the function mapping. To write this formally, we're going to use the more common way. So we'll do f of, we'll say a for area, equals to the square root of a times 4, or written in a more common way, 4 root a. All right. Now we can use this function, if we want, to find the perimeter of a square with area of 4. Just plug it in. We get f of 4 equals to the square root of 4 times 4, which is equal to 4 times 2, or 8. And we also have f of 6 for a square of area 6 equals to the square root of 6 times 4, which is just 4 root 6, because there are no squares in 6 to pull out. Once again, the full definition of our function is the description of the inputs and the outputs, and the rule that describes the mapping. Now, our third example might look a little abstract for now, but it'll come up and look familiar if you go under pre-calculus and start looking more at rates of change. In any case, it takes in numbers in some input set A that I haven't described, and it'll output into the real numbers. We'll come back and revisit the question of domain in a later video, but for now, let's just go through the process of finding f of 3, f of 2, and f of 1. So starting with f of 3, we just plug in, we get 3 squared minus 4 squared all over 3 minus 4, which is equal to 9 minus 16 all over 3 minus 4, or minus 7 over minus 1, which equals to 7. Going on to f of 2, we've got 2 squared minus 4 squared all over 2 minus 4, which equals 4 minus 16 over minus 2, which equals 2 minus 12 over minus 2, or 6. Finally, we've got f of 1, which is 1 squared minus 4 squared over 1 minus 4, which equals to 1 minus 16 over minus 3, or minus 15 over minus 3, which equals to 5. Now, if you want to look ahead and think about domain, I invite you to think about what f of 4 is, and whether it's defined, what it should be if it is. Otherwise, let's go on to example 4, which is another abstract example. Let's say we've got a function g that takes in whole numbers, represented by the z symbol for integers, and sends those whole numbers into the real numbers. So output could be any number. And its mapping is described by g of n equals n times n plus 1 over 2. Let's go through the process of finding g of 3, g of 5, and g of 6. So we'll start with g of 3. We have 3 times 3 plus 1 over 2 is equal to 3 times 4 over 2, which equals to 12 over 2, or 6. Moving on, we've got g of 5. Plug in again, we get 5 times 5 plus 1 over 2, which equals to 5 times 6 over 2, or 30 over 2, which is 15. We've also got g of 6, which is 6 times 6 plus 1 over 2, or 6 times 7 over 2, or 42 over 2, which is 21. Now, before we move on, I want you to take note of the fact that even though our mapping expression has a fraction in it, we never got a fraction out when we evaluated these inputs, right? We always ended up with a whole number, despite this divided by 2 that we have in the original definition. And I invite you, if you want, to look ahead to our discussion that's coming up on range, and think, when n is a whole number, as we've described, will the output always be a whole number? Give it some thought. But otherwise, that wraps up our examples. The main takeaway you should get from this video is that function mappings will be defined most often by rules that encapsulate the relationship between an input set and the output set, and that the function is usually written with describing this relationship in mind. And that's functions defined by rules. Thank you all for watching, and I'll see you next time.